Hi everybody, welcome to another IZN DWF arcade repair video. This time I've received quite a few boardsets to be serviced. Exactly 4 boardsets, each composed by 2 PCBs. All these boardsets are Atari Pole Position either 1 or 2, so I'm going to make a long pole position repair-a-thon, it seems. When working on similar or identical game PCBs, it's always a good idea to first check whatever can be checked, like for example all socketed static RAM ICs. This method also helps in finding hidden problems, like this pin that was bent outside the socket, and these other static RAM ICs that had too many broken legs. Of course, this is a very common IC, so not a problem to be substituted. Then I've spent a few hours dumping all ROMs to assess what board is what. And this also showed some problems. Look at this checksum for example. It changes every time I read the same EEPROM. So clearly this one needs to be erased and programmed again. Another very common issue on these boards are the NAMCO custom ICs like this one. They often have self-destructing pins, and in this case I'll try very hard to save as many as possible, since there are no cheap replacements for them. This step also required some hours in total, since each boardset has quite a few custom ICs. Sometimes, like in this picture, pin fragments were too short and I needed to sand down part of the IC case to make room for a good solder joint. It's also necessary to support the IC to make better solder joints with the replacement pins. Then all pins that didn't detach need to be gently cleaned from the oxide layer. I prefer to do it manually with a small file. All sockets must be inspected to find and remove pin fragments that detached from the ICs. A few ones kept on losing pins as soon as I was soldering the replacements. I'm prepared to reverse engineer the original ICs and try to make replacement ones if absolutely needed. Another common issue on pole position boardsets is burnt power supply pads. In this picture I'm soldering a new copper strip over the burnt one. Then the strip is cleaned again and trimmed with a sharp knife to leave the correct spacing to the adhesion contacts. Here's the finished repair on another board that had a similar damage. Of course, it's much better to use spade connectors that can be soldered in appropriate pads on both PCBs to connect the 5V and ground wires. I've also suggested to the owner of the boards to do a similar modification on the cabinet, so it will not be necessary to use anymore the edge connector for power input. Another preliminary step to service pole position boardsets is to make an interconnection cable between the CPU and the video PCBs. The original interconnect board forces the two PCBs to be stacked one on top of the other, and that is not suitable for troubleshooting. Luckily, the edge connectors are almost identical to the old PC ISA bus ones, so I've desoldered two ISA bus connectors from an old Amstrad PC that I was keeping for parts. Then I've joined the two connectors back to back by soldering individual wires and applied some hot glue to add mechanical stability. Notice that the pole position connector is actually one pad shorter than the ISA bus, so one position on both connectors has been blocked to allow proper mating to the PCB. Also, this step required a few hours of work. Another problematic area on a pole position CPU board is around the rechargeable battery. In all the boards I've got, the battery was already removed, but on all boards there were some visible corroded pins. However, the various problems and fixes will be shown separately for each board set. And last, here is a peculiar problem on 2 of the 4 board sets. See this Z80 CPU in position 4N? Well, it's the wrong IC. In fact, as we can see in the schematic, the correct CPU on 4N is a Z8002, which is a 16-bit CPU made by Zilog. In reality, a pole position CPU board has 2 Z8002 and the other one goes in position 3A. And guess what? Even on 3A socket we have another Z80 CPU. My assumption is that these boards were sold as non-working, but to make them look complete they added an IC that would look similar enough to the correct one. Of course, a Z8002 is much more valuable than a Z80, since it didn't see much use. However, a good replacement for it is the East Germany clone UB8002, that is also cheaper than the original Zilog IC, so I've ordered a few of them. This little PCB contains the steering wheel encoder circuit. A slotted cylinder can rotate inside this groove. This black assembly actually contains 2 infrared LEDs and 2 optical receivers. I'm going to simply check that both the output signals toggle as I block the light on one or both infrared sensors. First of all, let's check that the infrared LEDs actually work. Every digital camera has some sensitivity to infrared light, so we can easily see both LEDs glowing. Now, if I block one or both light paths, I have this first signal toggling. This must be likely the clock signal. Also, this other pin is toggling, and it's probably the data signal of this quadrature encoder. First of all, I don't have the appropriate slotted cylinder that goes into the encoder photointerrupter, that is part of the steering wheel mechanisms in the arcade cabinet. Luckily, the game can work with any quadrature encoder signal applied to inputs ST1 and ST2. Notice, however, that for some reasons they have designed 3.3 kΩ pull-down resistors on both inputs. Those 2 resistors pull more current to ground than what a typical old mouse phototransistor output can supply, so I needed to add a couple of transistor amplifiers on both outputs of this old mouse to have enough current for the pole position inputs. I have used this circuit on both the data and clock outputs. Any small PNP transistor works fine. You may notice that this is an inverting amplifier, but everything works fine as long as we invert both signals. The shifter and gas pedal inputs posed no problems, since the first one is just a switch and the other one is just a potentiometer. When I dumped all boards' ROMs, I've noticed that not all sets were the same. Luckily, MAME source file for these games has a complete list of all ROMs for both pole position versions 1 and 2. It turned out that 2 sets have pole position 1 ROMs, 1 set has pole position 2 ROMs, and 1 set is actually a Frankenstein board set with pole position 1 on the CPU PCB and pole position 2 ROMs on the video PCB. I decided to start with the pole position 2 board set. This is one of the board sets with a Z80 CPU in place of one of the Z8002. At this time, I hadn't yet received the replacement ICs, so I've just borrowed one CPU from a complete board. The other Z8002 socket, however, is correctly populated with the right IC. Around the battery area, some solder joints appeared corroded, so I've tried to refresh the worst ones by applying fresh tin, like for example on Q3 in this picture. At power on, we just have a garbage screen with some flickering characters. Now, in reality, there are 3 CPUs on a pole position board, and the third one is an old 8 bits Z80. This one is the first that starts and does some RAM and ROM tests before lifting the reset lines to the Z8002 ones. So if all appears stuck, we must first check what's happening around the Z80, as always starting with clock and reset signals. The reset signal to the Z80 doesn't look good. First of all, it's pulsing, probably because the CPU is not able to reset the watchdog circuit. But also notice how the low level is not really going down to 0 volts, and that's a problem. The Z80 reset circuit, including the watchdog counter, is circled in red. I can already see a potential problem. Notice that when the watchdog counter overflows, one CMOS inverter gate is supposed to discharge a capacitor through a diode. However, typical 4000 and 4500 CMOS gate current sink is very low. From the datasheet, we see in fact that the 4584 sink current at 5 volts supply is quite low when going down to 0 volts. Typical is less than 1 mA and gets lower as the IC temperature increases. However, the same capacitor is continuously charged from the 5-volt rail through a 2.2 kΩ resistor, and that means that if the capacitor will reach 0 volts, the charging current will be 2.2 mA, which is likely much more than what the CMOS gate can sink at that voltage. The circuit may work just fine if the watchdog is not continuously kicking off anyway. So the incorrect low level is a problem caused by a not so good design choice. The good news is that the 4584 is a pin-to-pin compatible with the other CMOS inverter ICs. And there is one CMOS family that can drive much higher output current at 5-volt supply, so I can use a 74HC14 in place of the 4584, and that will likely solve the bad drive level. In fact, after the substitution, the low reset level goes down to 0 volts, but of course the watchdog is still continuously resetting the Z80, so the overall situation didn't change. At this point, having found no evident stuck signal on the Z80, I decided to install an op generator socket. If you are not familiar with this tool, you'll find one video link about it down in the description. Since almost all address decoding logic has been implemented with one single PLD, I'm going to check that with the op generator installed, all outputs of this IC, so pin 12 to 19, are toggling. 12 OK, 13, 14, 15, 16, 17, it is stuck high, 18 is OK, and 19 OK. Pin 17 is labeled RAM CS, so it is a chip select for some RAM IC, and it's not good that it never toggles with an op generator socket. So I'm going to remove the PLD IC. The original IC is an 82S153 PLD, which is a one-time programmable part. Luckily, someone else already reverse engineered the PLDs on the pole position CPU board and provided the equations. As always, relevant links are down in the description. So I've just written a CUPL source file with the equations, and now I can compile them for any pin compatible part, like the very common GAL16V8 IC that can be erased and programmed many times. And here is a suitable IC found in my spare programmable logic devices bag. And yeah, with the new address decoder, the boardset starts fine and runs the attract mode. So far, so good. Like in many other arcade games, this one has a good service menu. All inputs can be tested. And we can trigger all the various sounds of the game. There doesn't seem to be any problem, so this first boardset was easily repaired, and I hope you find it interesting and that you learned something. I'll try to play again, even if without the proper controls it won't be too funny. It's all for this video. Have a nice time and thank you for watching.